Today's lesson is called Multiplying and Factoring Polynomial Expressions, Day 4. So first, let's read the paragraph about using the GCF. If the leading coefficient for a quadratic expression is not 1, the first step in the factoring should be to see if all the terms in the expanded form have a common factor. Then, after factoring out the greatest common factor, it may be possible to factor again. A polynomial is factored completely over the integers when all of its factors are prime. So again, some things I want to point out here. If it's not a 1, the first step should be to see if they have a common factor. Then, after factoring out the greatest common factor, you might have to factor again. A polynomial being completely factored means that everything is prime. And remember what prime means. You only have factors of 1 and itself. So today's lesson I also like to refer to as factoring completely. This really is what we're going to tackle today in the lesson. Learning the order of steps to look for so that you can take an expression and have it in a completely factored form. So example 1 really guides us through this. To factor 2x cubed minus 50x completely, the first thing we want to do is see if there is a GCF to factor out. When I look at this expression, the leading coefficient there of that first term is 2, and I want to see if there's a GCF that I can take out in order to make that next expression factorable. So the GCF of the expression, I want to look at 2x cubed and 50x. The greatest common factor number-wise between 2 and 50 is 2. And if we're looking at powers of x cubed and x, remember you're always going to take the smallest power. So that would be 2x, or x to the first. So now we're going to take that and factor it out. I know I'm going to have 2x outside of a set of parentheses. If you think back to what we learned, we're taking basically each of these and dividing by that GCF. So if I factor out 2x, I should have x squared left over first, and then negative 50x divided by that 2x is going to be negative 25. So there's my first expression factored only using the GCF. Now when I look at that expression, it is not factored completely. Inside of the parenthesis, I have dots. Remember, difference of squares, difference of two perfect squares. So I need to now factor that part down again. I'm going to keep the 2x, but then I'm going to take my x squared minus 25. We know it's going to factor into two binomials. The square root of x squared is x, so that goes in the first position. The square root of 25 is 5. That goes into the second position. And remember, when you're factoring a difference of two perfect squares, one is plus and one is minus. It does not matter which one is which. So this is my fully factored expression. If I look at each piece, it is definitely prime. There's nothing else that would go into it besides 1 and itself. So now let's look at example 2. Follow the steps to factor negative 16t squared plus 32t plus 48 completely. So again, when you're thinking about order, GCF is always first. So first, factor out the GCF. Remember that when you factor out a negative number, all the signs in the resulting factor will change. So remember that we want that first term to be a positive 1. So looking at our first term, I think I want to get and divide out that negative 16. I need to look into the rest of the expression and see if that works. Is negative 16 actually a common factor? It is. It's the greatest common factor between all three of those terms. There is no variable because the last term there, 48, has no t. So our GCF here is just negative 16. So I'm going to take negative 16 and divide it out. That would leave me with t squared minus 2t because of the negative that we took out, and minus 3. Now, unlike our first example, I do not have a remaining dots inside, difference of two squares, but I do have a trinomial that we can factor. So it says, now look for ways to factor further. So inside there, I have a trinomial that needs to be factored. So remember how we do this. We're going to list the factors of the last number. So negative 3, my factor pairs would be 3, 3, and negative 1. Also negative 3 and positive 1. We want to pick the pair that's going to add up to the middle number. Our middle number is negative 2. So I want to pick this pair because negative 3 plus 1 equals negative 2, which is our middle term or our B value in the term. So now I'm going to keep my negative 16. Once you factor out that GCF, it can't disappear. And you're going to have t minus 3 and t plus 1. Now, of course, again, you can have those in a different order. You could have negative 16, then t plus 1, then t minus 3. Remember that multiplication is commutative. Now in example 3, it says factor x to the fourth minus y to the fourth completely. Okay, so again, our first step is to look for the GCF. But when I look at x to the fourth minus y to the fourth, there is no GCF. So we're going to make a quick note here that there's no GCF. I still need to look for that first, but looking at that, no GCF. So now we look on for our other types of factoring. Is there dots? Is there trinomial factoring? Okay, so that's your order. When I look at that, I see a difference of 2 perfect squares. Remember that it's perfect square if the exponent is even. So this is actually dots. So this is going to get split into 2 binomials. The square root of x to the fourth is x squared, so that goes in the first position. The square root of y to the fourth is y squared. That goes in the second position. 1 is plus and 1 is minus. So this is an example of me using difference of 2 squares. Now when I look at this again, I still don't have any GCF. We know that from before. I don't have any trinomials. The first binomial, x squared plus y squared, is already in its final form. However, when I look at the second binomial, that's another difference of 2 squares. X squared and y squared are perfect squares and they have subtraction. So I actually need to do dots again. And that can happen. You can repeat the type of factoring. So we would end up with x squared plus y squared. And then we'd have x plus y and x minus y when we factor that from dots. And now that is my final factored form. That concludes all of our examples for this lesson. On the next page are practice problems. You can go ahead and pause the video, try the practice problems, then resume the video to check your answers. If your teacher has given you an activity to do instead, this concludes your part of watching the video. So again, at this time, if you are completing the practice, please pause the video and then resume when ready to go over the answers. Okay, now that you've had time to try the practice, we're going to go over the answers. In number 1, 2y squared minus 8, you have a GCF of 2 as your first step, which leaves you with y squared minus 4. That's a difference of 2 squares, so it turns into 2 times y plus 2 times y minus 2. In number 2, you do have a GCF. You should be factoring out of 3. That gives you a trinomial remaining. So I'm going to list the factor pairs of negative 8 and find the pair that adds to the middle number, which is negative 2. You can see I circled the pair that works, 2 and negative 4. So your final answer by factoring your trinomial should be 3 times x plus 2 times x minus 4. In number 3, x to the fourth minus 16 is a difference of 2 squares. So that factors into x squared plus 4 and x squared minus 4. Then x squared minus 4 is still a difference of 2 squares. So you need to repeat the dots process to break that down into x plus 2 and x minus 2. In number 4, you have a GCF of 9n squared, leaving you with 9n squared minus 100, which is a difference of 2 squares. So that factors down into 3n plus 10 and 3n minus 10. Make sure you keep that GCF along the way and include it as part of your final answer. In number 5, a to the fourth minus 9 is a difference of 2 squares. Once you're done, for the first time in a while, you have to be careful. This isn't always going to end up in a double dots. A squared minus 3 is not a difference of 2 squares, so this is completely factored as it is. And then lastly, number 6, you're going to factor out a GCF of 10. That leaves you with a trinomial. Now, this trinomial was a pattern trinomial, so this should be y plus 5 and y plus 5. If you really need to go ahead and do your factoring, you would write 25 and list your factor pairs of 25. And then you're picking the pair that adds up to 10, which is where you get your 5 and 5. So your final answer should be 10 times y plus 5 times y plus 5. And that concludes your lesson on multiplying and factoring polynomial expressions, day 4.